One interesting application of exponential equations is growth models. And nothing grows as well as natural phenomenon, like bacteria. So in this example, we have some bacteria culture, and it's growing at a constant rate. Now that's key. It has to grow at a constant rate, and the rate has to be proportional to the amount of bacteria there is. And when those conditions exist, you have an equation called P equals P initial e to the RT. You probably recognize this, and we know how to deal with exponential equations by now. But I'm going to just go over the basics of what this thing on the left is compared to that exponential equation on the right. Now, P0 that I've written right here, that's your initial population, whatever that population is, in this case, bacteria. So I would put that right here. In this example, that's 930. Now, R is your growth rate, okay? And in this case, that is 0.47. So what 0.47 refers to is 47%, right? So we would just be careful to write it that way. This is the old deal where 47%, you divide it by 100 and you turn it into a decimal. Okay, so that's 0.47. And to calculate the population after 8 hours, okay, this last part right here, what that means is I'm basically evaluating this equation. So I say P, and if you want, you could say P of 5 hours, I could write it that way, equals your initial population, 930, times E to the R, and remember R is that 0.47, T. And here's the important part. T is that 5 hours. Okay, that's what P of 5 means. This P over here, I should have written it a little better. I should have written it as in P as a function of T. Okay, so let's just go ahead and evaluate that. And you're going to want a calculator for this. It's not too easy to do in your head. Just punch those numbers in. Please don't round off halfway through. And let's see what we get here. We get 9,752. Okay, so that would be how many bacteria are in this example.